Alright, so now I want to prove the next theorem, which is that A is an open subset in R if and only if A is the union of countably many disjoint open intervals. So here is the proof of this. Now notice one thing is that there are two statements that we need to show. One of them is that if A is the union of countably many disjoint open intervals, then A is an open subset of R, which we already have talked about. Recall that before I showed to you that the union of any collection of open sets is open. Now, since open intervals are open subsets of R, therefore, if A is the union of countably many disjoint open intervals, then A is an open subset of R by what we have done before. So in order to prove this theorem, I have to show the other direction, which is if A is an open subset in R, then A is the union of countably many disjoint open intervals. So we assume now that A is open in R. It's an open subset of R. We have to show that A is the union of countably many disjoint open intervals. Now, so here's how we can find open intervals. So let X in A be an arbitrary element Now, since A is open, we know that there are open sets containing X that are inside of A. So since A is open and X is in A, there are neighborhoods of X which are inside of A, which means there are open sets. There are open intervals containing X that are in A. So since A is open, there are open intervals there are open intervals containing X that are inside A. So let's let Ix be the largest open interval containing X that is inside of A. So Ix is the largest open interval containing X that is inside A. Well, more precisely, what we are saying here is that what Ix is, let's say, um, more precisely I can say the following. Let Ax be the infimum of the set of all numbers A, such that the interval from A to X is inside A, or Ax is negative infinity. So what am I trying to say here? I take Ax to be the infimum of the set of all A, such that the half open interval from A to X is inside A. If this set of A does not have any lower bound, then I take Ax to be negative infinity. Similarly, I take Bx to be the supremum of all B, such that the interval, half open interval from X to B, is inside A, or Bx is infinity. Once again, Bx is taken to be the supremum of the set of all B, such that the half open interval from X to B is inside A. If this set of all B does not have an upper bound, then we take Bx to be infinity, and then Ix is basically the interval from Ax to Bx. Okay, and so what we are saying here is that I have some number Ax, some number Bx, and X is, say, X is, so Ax to Bx is an open interval containing X, and this is inside of A. So Ix is an interval containing X that is completely inside of A. So then it's clear I could say that A is equal to the union of all these Ix. Okay, because that every Ix is inside of A, and for any X is in A, for any X inside of A, X is in the union also. So A is clearly the union of all these intervals Ix. Now the question is, there are two more things to show. One is that if I define, let me define, let's see, I don't know, maybe I will, let's let S to be the set of all these Ix, such that X is in A. Remember, I have already written A as a union of open intervals, but what I have to show is that I have only countably many intervals there, and they are disjoint open intervals. So how do I show that S is a disjoint? The intervals in S are disjoint, and how do I know S is a countable collection of open intervals? So to do that, this is what we are going to do. First of all, why are the intervals Ix, why are the intervals in S are disjoint? Well, this is what I claim for any xy in A, either either Ix is the same as Iy, or Ix intersected with Iy is empty. So for any xy in A, either Ix is Iy or their intersection would be empty. So how do we show this? Okay, so to prove this claim, so if either they intersect, either Ix and Iy, they are empty. Either the intersection of Ix and Iy is empty, or it's non-empty. So I want to show that if it is non-empty, they have to be the same. So if Ix intersected with Iy is empty, then of course then we are done. Then we are done, because my claim is for any xy in A, either Ix is equal to Iy or Ix intersected with Iy is empty. So if the intersection is empty, then we are done. If the intersection is not empty, then we need to show, Ix is the same as Iy. Well, so why is that the case, that Ix is the same as Iy if their intersection is non-empty? Well, let's make a figure here, that if I have, let me draw Ix. So Ix is from Ax to Bx. Okay. Now, so recall that Ix is from Ax to Bx. That's what our notation was. And then Iy is Ay to By. Now, the question that we want to ask is the following. Is By bigger than Bx? So, do we think that By is bigger than Bx? Well, if By is bigger than Bx, then since Iy intersects Ix, that would mean that Ay must lie to the left of Bx. Okay. Well, if Ay then lies on the left of Bx, then notice that the interval from Ax to By, that interval contains x, and that interval would also be entirely inside of A. But that contradicts the fact that that the interval Ix was the largest interval containing x that is inside of A. So we can't have a bigger interval containing x inside of A. So By therefore can't be bigger than Bx. In a similar way, we can argue that By cannot be smaller than Bx, and therefore Bx and By must be the same. And you argue in the same way that Ax and Ay must also be the same. Okay. So that tells us that if Ix intersected with Iy is non-empty, then Ix and Iy are the same. So now what we have is that if I look at the set S equals to the set of all Ix, x is in A. This is a set of disjoint open intervals. Once again, of course, there might be two different values of there might be two different values in A for which you get the same interval. Okay, but those intervals are counted only once in S. So S is a set of disjoint open intervals. Now, how do I know that S is countably infinite? Why is S countable? Well, let's let Q be an enumeration of the rational numbers. So R1, R2, R3, dot dot dot. So this is an enumeration of the rational numbers, and the set of rational numbers is a countable set. And notice by the density theorem, Ix contains, for any x, Ix contains rational numbers. So for any x, Ix contains rational numbers. So what I'm going to do is that for any x in A, for any x in A, let n x be the least positive integer for which R and X is inside of Ix. Since Ix contains many rational numbers, I am just picking the rational number in Ix which has the least index from this enumeration. Okay, and then I claim Ix is exactly the same as I, R, and X. And this follows from what we have done before, because Ix and I, R, and X, they have the rational number R and X in them. So that is, since R and X is inside of the intersection of Ix and I, R, and X, by what we have proved right here before, right here, that by that argument we see that they have to be the same. Because once again, recall here we said if Ix intersected with Iy is non-empty, then Ix and Iy must be the same. So that's why we could say that Ix and I, R, and X, they are the same open intervals. So that shows that from the set So this shows that every ix, so it shows that every ix corresponds to certain I, R, and X, where I, R, and X is a rational number. Well, that simply says that S, which is the set of all Ix, such that X is in A, this is countably infinite. And then we are done.